You know, when most of us picture artificial intelligence, we tend to imagine this massive omniscient brain sitting in a server room somewhere.
Right, like a giant supercomputer.
Exactly. You ask a question, the giant brain churns through, petabytes of data, and it just spits out an answer. It's a very comforting, very contained image, just a single mind at work.
It is comforting, but it's increasingly outdated. That whole monolithic intelligence model is rapidly being replaced.
Right, because the second you step into the real world of modern AI development building, things that actually run enterprise pipelines, that giant brain completely shatters.
Yeah, it breaks apart into pieces.
Right. We aren't looking at one AI anymore. We're looking at an entire ecosystem of highly specialized agents. You've got planning agents, coding agents, testing agents, and security verifiers, all supposedly working together.
And that transition from a single model to a team of agents introduces an incredibly complex, really messy coordination problem.
Which is exactly the problem we are tackling today. Welcome to the Deep Dive. We're exploring the foundational state-of-the-art research driving generative AI, and today our mission is looking at a fascinating new preprint paper titled Learning to Hand Off: Provably Convergent Workflow Learning Under Interface Constraints.
It's a dense title, but a massive breakthrough.
It really is. Because the real issue here is, how do you get these specialized AI agents to work together when they belong to different companies, operate across different servers, and flat out refuse to share their private data?
Yeah, you're trying to teach a team to collaborate when everyone is essentially wearing a blindfold.
Exactly. Okay, let's unpack this, because to really grasp the magnitude of the breakthrough here, we need to understand the gap between how developers want to build these workflows and how they actually have to.
Right, so if you're building an AI pipeline, in a perfect world, you'd use what the researchers call the centralized regime.
Which is basically the laboratory setup, right?
Yeah, exactly. In this scenario, you are the omnipotent designer. You have this God's eye view of everything your agents are doing. You see all their internal trajectories, their scratch pads, their hidden parameters.
And when you have that level of perfect information, optimizing the workflow is basically a solved problem.
Entirely. You can perfectly tune how Agent A passes data to Agent B because you see exactly, step by step, how Agent A came to its conclusions.
But the real world is not a laboratory. If you look at actual production systems, frameworks like MetaGPT or Agent Coder, they operate in what the paper calls the sequential decentralized regime.
Right. They don't run in parallel, and there is absolutely no omnipotent designer watching them.
They just pass one artifact at a time down an assembly line.
And the constraints on that assembly line are severe, largely because these pipelines span major trust boundaries.
Let me see if I'm tracking the practical reality here. So, say you're a hospital using an AI pipeline to process patient records. You might use a local, highly secure agent to strip out personal data and then pass those clinical notes to an external proprietary LLM for the actual diagnostic analysis.
Yes, that's a perfect example.
And the external vendor legally cannot see your internal agent's process. Plus, the vendor isn't going to let you see inside their proprietary model's weights frame.
Precisely. You're dealing with safety filtering, medical compliance, API contracts. Vendors protect their prompt templates as highly valuable intellectual property. No one holds the joint trajectory data.
Wow.
Yeah, you cannot see the internal chain of thought of the agent that came before you or the one that comes after.
So if the centralized approach is like having a micromanager who can watch every employee's computer monitor simultaneously, this decentralized reality is more like a corporate relay race where every runner is blindfolded.
That's a great way to put it.
They wait, they get handed a baton, they run their specific leg of the race in total darkness, and they hand the baton blindly to the next person. They only know what the baton feels like and their own private thoughts.
Exactly.
But wait, that raises an enormous red flag. How can you possibly optimize a workflow if no single entity actually sees the whole workflow?
What's fascinating here is that the researchers realize this blindness is a feature of modern AI ecosystems, not a bug.
A feature.
Yeah. The traditional approach is to try and break down the walls to get more visibility. This paper says, no, we have to keep the walls up and work purely within the constraints.
Because the existing mathematical frameworks for AI training completely collapse under these specific blindfold conditions, right?
Exactly. The paper actually walks through the graveyard of older frameworks that fail here. Let's start with DEC-POMDPs.
Oh boy. DEC-POMDPs. That stands for Decentralized, Partially Observable Markov Decision Processes, right?
Oh, it's a mouthful, yeah. But it's the classic model for cooperative multi-agent control. Think of like a swarm of drones flying together.
Okay, drones.
The fundamental assumption of a DEC MDP is that agents take actions concurrently at the exact same time, and they share a joint reward pool.
Which instantly violates our assembly line reality. If my planning agent finishes its task on Tuesday and hands an outline to my writing agent who finishes on Wednesday, they are acting sequentially, not concurrently.
Right. You can't use swarm math for a factory line.
Makes sense.
Yeah.
So then developers try to use the options framework.
Yeah, and the options framework handles actions that take different amounts of time, which fits our sequential problem, but it assumes there is a single meta-controller, a manager, that observes the full state of the system at every decision point.
And we just established that the God's Eye View manager doesn't exist across corporate boundaries, so that's out.
Right. Then you have some of the newer practical systems like AgentNet. They try to navigate this by using hand-designed rules. Basically, developers writing hard-coded heuristics to route tasks from agent to agent.
But heuristics are just, what, educated guesses based on moving averages?
Exactly. They lack any rigorous mathematical guarantee. The pipeline might optimize over time, or it might just get stuck in an endless loop of passing a task back and forth forever.
Yikes.
Without a mathematical foundation, you just can't guarantee convergence. So the researchers had to throw out the old math and build an entirely new decision-theoretic foundation from scratch.
Okay, let's dive into that new foundation. Because to survive strict privacy, they introduce a formal model called the SMDP. That stands for the Interface-Constrained Semi-Markov Decision Process.
Right, and it operates entirely at the handoff times between agents.
And to understand it, we have to look at the three distinct layers of state they define. First is the global latent state. This is the ultimate reality of the task, like the full picture.
And crucially, no agent ever sees this.
Right. Then second, you have the private state.
Which is the local environment of the individual agent. It's the agent's internal memory, its proprietary logic, the local files it accesses, all entirely hidden from everyone else.
And third, you have the interface state. This is the artifact itself.
Yes, the piece of code, the text summary, the mathematical proof that is actually handed across the boundary. This creates the interface constraint.
Meaning Agent A cannot see Agent B's internal thoughts, and Agent B only gets the artifact passed from Agent A.
Exactly. And building on that strict boundary, the researchers designed a decentralized algorithm they call ICQ. It's an asynchronous Q-learning algorithm.
Now, just as a quick refresher, Q-learning is a foundational reinforcement learning technique where an AI learns to assign a value to a specific action, right? Over time, it maps out the best path by choosing the highest value actions.
Spot on. But to calculate that value, standard Q-learning relies on seeing the whole environment.
Right, so if the agents can only see the interface artifact, how do they learn the value of passing a task to someone else?
The paper details this mechanic called value passing at handoffs. And this is brilliant. At the exact moment Agent A hands the baton to Agent B, the cross-agent coordination is restricted to a few tiny things.
Right. The artifact, the duration of the task, the reward, and literally a single scalar number.
Yes. Just one number. The bootstrap target.
Okay, wait. I have to push back hard on this. You're telling me you have an incredibly complex large language model doing advanced calculus or writing thousands of lines of Python, and it coordinates its workflow training by passing backward just a single digit.
I know.
Is one scalar really enough bandwidth to teach a blindfolded team how to optimize a complex workflow?
It sounds counterintuitive, I completely agree. But yes, it is entirely sufficient. To understand why, you have to look at what that single number represents. It is the successor agent's localized max value calculation.
Meaning what, exactly? Walk me through a handoff.
Okay, imagine you are Agent A, a software architect. You draft a high-level system blueprint and hand it across the interface boundary to Agent B, the coding agent.
Okay, I passed the blueprint.
Agent B receives that blueprint, analyzes it against its own private state, its own hidden capabilities, and its past history of success. Agent B calculates an internal expected success score for turning that specific blueprint into working software.
Oh, so Agent B is essentially grading its own confidence.
Exactly. And Agent B simply passes that final confidence score, that single scalar number, back across the boundary to you, Agent A. You don't need to know how Agent B writes the code or what logic it used to arrive at that score.
I just need to know that when I pass this specific type of blueprint, the downstream success value is, say, 8.5 out of 10.
Exactly. By keeping the calculation local and only passing the result across the interface boundary, ICQ perfectly respects vendor privacy while mathematically optimizing the workflow.
I think I get it. To use an analogy, it's like a restaurant kitchen. The head chef is expediting orders. The head chef doesn't need to read the grill cook's mind to know exactly how the steak is being seared.
Right.
The chef just looks at a tick at the interface state, and if the grill cook shouts back 5 minutes, that's the scalar value. The chef optimizes the rest of the kitchen based entirely on that one piece of compressed data.
That is a perfect analogy. That's exactly how it works.
Okay, so passing a single scalar works beautifully in theory. But, if I'm a developer spending massive amounts of money on API calls to train these systems, I can't just deploy this and hope it eventually learns. I need proof.
You need a guarantee. And that transition from clever mechanics to rigorous mathematical guarantees is really what makes this paper a landmark. They didn't just build an algorithm, they proved it works under bounded conditions.
Which is a first for this type of decentralized partial observability, right?
It absolutely is.
Here's where it gets really interesting. The paper introduces Theorem 1, which provides a finite sample guarantee.
Yes.
And if you're building an AI deployment on a bounded budget, this is your holy grail. It tells you exactly how much sample budget is enough, not just that it will converge at some point in the distant future.
Exactly. And Theorem 1 breaks the potential errors down into 3 independently controllable sources.
It's like a project management budget with 3 specific line items you have to manage.
Right. So let's walk through those 3 dials. The first is the neural function approximation error.
Which basically boils down to the quality of your tools.
Exactly.
Yeah.
How good is the neural network inside the agent at estimating values? If you use a sufficiently large and capable network, this error essentially vanishes.
Okay, so dial number 2 is the interface representation gap, which they call the AIS gap.
Yes, AIS stands for Approximate Information States.
And this is the literal price you pay for the privacy constraint, the price of the interface constraint. It's the penalty for your agents being blindfolded.
Right. If the interface state they pass back and forth is too compressed and misses critical context, this error goes up. You've stripped away too much information.
Got it. And dial number 3 is the mixing time residual.
This is a temporal error. It's driven by the fact that the algorithm simply needs time to explore different paths to find the best one.
Driven by the random duration of agent tasks, right?
Exactly. Crucially, as you run the system longer and collect more samples, this residual error predictably decays towards 0.
But hold on, because there is a massive catch here that we need to unpack. If task durations are random because, one AI might take 2 seconds to answer a question, and another might take 20 minutes to write a script, how doesn't that completely blow up the math? Standard Q-learning assumes steps happen at fixed intervals.
If we connect this to the bigger picture, you've just hit on the central technical novelty the researchers had to pull off. In standard reinforcement learning, you rely on a fixed discount factor to value future rewards.
Like calculating compound interest.
Exactly. A reward today is worth more than a reward tomorrow. But imagine trying to calculate compound interest when you don't know how long a year is, and every year is a randomly different length.
Oh, wow.
Right, because the time it takes an agent to complete its task is a random variable. The discount applied to the future reward becomes a random variable.
So wait, what does the paper mean when it says they proved a Bellman contraction under a random discount? That is incredibly dense jargon.
I know, let's break it down. The Bellman equation is the core math behind Q-learning. It basically says the value of your current state is whatever immediate reward you get, plus the discounted value of wherever you end up next.
Okay.
A contraction just means that as the algorithm updates, the errors shrink, and it aggressively zeroes in on the optimal true value rather than spinning out of control.
So if the time delay is random, the discount fluctuates wildly, and normally that would cause the math to spin out of control.
Right, the variance would normally explode.
Oh.
But they achieved something highly novel. They mathematically proved that even with a random discount factor, they could successfully absorb that duration distribution into the mathematical operator.
Meaning the system still strictly contracts, the errors still shrink.
Yes, it is mathematically guaranteed to find the optimal workflow, even with random task times.
That is heavy, brilliant math. But, equations are just equations until they meet reality. I want to look at the real-world evidence. The researchers ran 4 experiments to prove that this decentralized algorithm, ICQ, matches a centralized oracle without breaking the rules.
The headline experiment here is their multi-LLM math reasoning test. This is where we see it all come together.
Yeah, they created a pipeline of 4 specialized agents powered by GPT-4 Mini.
Right. You have a commissioner who initiates the task, a thinker who drafts step-by-step rationales, a checker who verifies the logic, and an editor who formats the final answer.
And here is where the interface constraints become super tangible. The artifact passing between these agents isn't just a simple number. It's a massive, high-dimensional text conversation.
But to make the routing efficient, ICQ compresses that entire wall of text into a simple 4-bit AIS observation.
Yeah, just 4 bits.
Yeah, it strips away all the nuance of the math problem itself and reduces the state to 4 binary questions. Is the answer given? Has it been modified? Has it been checked? Is it judged correct?
Oh, it's back to the restaurant kitchen ticket. The expediter doesn't read the recipe, they just look at 4 checkboxes. And based on just those 4 bits of information, we see this amazing dynamic discovery.
Yes, what it discovers changes completely depending on the difficulty of the environment. They tested this pipeline on highly complex data sets, like MathQA and MMLU high school math.
And on the hard math, the ICQ algorithm learns very quickly that it must route the draft from the thinker over to the checker agent before the editor touches it.
Right, it realizes that complex problems require verification.
But then they threw it a curveball and tested it on MMLU elementary math.
And on the easy math, the algorithm realizes that sending the draft to the checker agent actually introduces errors. The checker overthinks the simple arithmetic.
So the AI manager actually fired the checker agent for the easy math because it was overthinking and messing up the answers. That is incredibly human.
It really is. It learns to bypass it entirely, using simple chain of thought directly from the thinker to the editor. Because ICQ was able to recover the best predefined workflow dynamically on every dataset without a central planner, it proves that decentralized agentic workflows can self-optimize purely through the interface constraints.
That's just wild. And they briefly mention other experiments proving robustness too, right? Like the synthetic IC SMDP.
Yeah, that one manipulated a retention ratio to prove the AIS gap math exactly.
And the multi-agent routing test, 100 agents perfectly routing on networks.
Yes, finding the optimal path perfectly.
And my favorite, the multi-agent CPU programming test. 6 agents mimicking CPU parts like loaders and logic units.
Proving adaptability on entirely unseen targets. It really proves the system's robustness across the board.
So what does this all mean? If you're listening to this, generative AI is moving away from a giant brain into specialized teams. Multi-agent LLM systems are the future. And this research proves we don't need a massive privacy-destroying eye in the sky to make them work perfectly.
No, we don't.
They can learn to collaborate efficiently while keeping their inner workings entirely private, which is absolutely huge for cross-company AI pipelines.
It is, and this raises an important question. If independent, highly specialized AI agents can achieve perfectly optimal collaboration by sharing nothing but a single, highly distilled number at their handoff points, what does that say about human organizational structures?
Oh, man. That is a deep thought.
Seriously, are our endless status meetings and demands for total transparency actually making us more efficient, or are we just failing to design a good enough interface constraint?
Wow. We started today talking about how comforting it is to imagine a single monolithic brain, but it turns out a team of blindfolded specialists passing a baton and a single number in the dark might just be the most efficient way to build the future. Thank you for joining us on this deep dive. Keep questioning, keep learning, and we will catch you next time.